Hello everyone, my name is Jared Levinson and today we'll be going over volume by slicing. The main concepts we want to go over with volume by slicing all start out with this basic formula which reads the volume is defined by the integral from a to b of our a to x function and dx, of course. So now after that, let's break down the specifics that we'll be using to manipulate this formula to specifically solve our volume by slicing problems. Now the first specific deals with volume by slicing by squares, which is simply defined by your side length squared. Now what we would be doing is taking the side length squared and plugging that back into the previous formula where we discussed with that a of x function. And we're going to relate that back to the original function they give us in the problem. Now moving on to the next specific deals with volume by slicing by semicircles, which is by pi over 8 times your diameter squared. Then equilateral triangles, which is square root 3 over 4 times the side length squared. And lastly, isosceles right triangles, which is going to be 1/2 of the side length squared. Now there's a couple things to note with the breakdown of these specifics. One thing to note is that it's always going to be either the side length or diameter squared in all of them. You're never just going to have the side length by itself for the main bulk of the problems. The only thing that's different between them all is the best way to describe it is this ratio that we're multiplying by. For example, with squares, it's only 1. With semicircles, it's pi over 8. Equilateral triangles, it's square root 3 over 4. And isosceles right triangles, it'd be 1/2. The best thing to do with these problems is probably to memorize the breakdown of these ratios. For example, associating semicircles with pi over 8, equilateral triangles with square root 3 over 4, etc. And the best way to just memorize that, and then you'll be very much prepared for volume by slicing problems. Now let's move on to some examples.
Let's look at a problem. We're going to find the volume of a solid whose base is bounded by the circle x squared plus y squared equals 4. Its cross sections perpendicular to the x-axis are squares. So you can see the graph set up right here on the left. What we're going to do is we're going to use this graph to cut square cross sections out of the circle and then find the volume of the solid whose base is that circle. So the first thing we need to know is that the area of the square is going to be s squared. You can see s there on the graph. Now, the other thing we have to know is that s is equal to 2y, and I already have y set up for, so y is equal to the square root of 4 minus x squared. But s is going to be equal to 2 times the square root of 4 minus x squared. Next, we know that the volume of the solid is going to be the integral from -2 to 2 of s squared. And the volume, as you can see, would be the integral from -2 to 2 of 2 times the square root of 4 minus x squared. If you plug that into your calculator, you get the answer of 12.57 square units. So that's how to solve that one. Now let's do a problem where we find the volume of the cross-section perpendicular to the y-axis of a right triangle are semicircles. So now we're going to be looking at this graph here on the left, where y is equal to 4/3 x minus 3. And you can see the semicircles I have drawn in there. That's what the cross-section is going to look like. So what we know is that the area of a semicircle is pi times the diameter squared over 8. Now in this problem, instead of the diameter being y, the diameter is going to be x, because we're looking at the perpendicular axis to the linear graph. So that's going to be the x value. So where we're given y, we have to solve and isolate for x. So as you can see, x is equal to 3/4 y plus 9/4 when you isolate for x. From there, we can take the volume by using the integral from -3 to 0 of pi times the diameter squared over 8. And that will be pi over 8 times the integral from -3 to 0 of 3/4 y plus 9/4 squared dy. So this time we're integrating with respects to y instead of x. If you plug that into your calculator, your answer is 1.99 square units.